Now, we know that when we deal with vectors in 2 and 3 dimensions, we can talk about the length of vectors. We can also talk about the angle between vectors. So in this section, we're going to be talking a little bit about these two concepts in n-dimensional space. Now, when you take the length of a two-dimensional vector, you go back here to see what we're doing here. If we take the length of a two-dimensional vector, well, let me just plot this in here. So here's a vector here. If I want the length of this vector, then I have two components here. I've got a component here, which I could call it x1, and here I have x2. And you know that the length of this is going to be the square root of x1 squared plus x2 squared. Now remember, this 1 and this 2 are the superscripts that denote which component of the vector it is. Well, we have this general form from the Pythagorean theorem. Now in 3 dimensions it works out the same. It's harder to draw, but just you would have 3 points here, and then you'd have x1 and x2 and x3. And it's a little bit hard to draw, as I said, but this x1 and x2 would give me something here, and then I go straight up to get the x3. And I get some vector here that goes out to this point. And it has 3 components, an x1 component, x2 component, x3 component. Sorry, that should be a superscript. And the length of that vector is just going to be the square root of x1 squared plus x2 squared plus x3 squared. Now, natural generalization, if I have n-dimensional space, is simply to take the square root of the squares of all of the components. So that's what we're doing here. He uses the letter v instead of x, but it's the very same thing. All right. Now, using the law of cosines, you can have an angle between two vectors. Okay. So here we have a vector v starting from here, vector u here. This double bar represents the length of v, the length of u, and here's the length of v minus the length of u. Why is this v minus u? Well, v plus u would be go out v this way and then go parallel to u the same direction here. So v plus u would be something out here. It would be this vector up here from this point to this point. Now it's v minus u because what you're actually doing to get this vector is you're going, if you go along v and then go minus u is the negative of this. Right? Go along v and go minus u, then you end up with a vector that's exactly parallel to this one. Okay, so this is v minus u. And this is the length of v minus u. Now the law of cosines says that the length of v minus u squared is the length of u squared plus v squared minus 2 times uv and cosine of theta. Now, they do this in 2 dimensions. This is going to be our definition of cosine theta. This is going to define what the angle is between two vectors. Now, it turns out that this definition works in 2 dimensions, works in 3 dimensions, and makes sense in higher dimensions as well. Right? So we don't define cosine first in its direction. We define cosine in terms of this algebraic relationship. Because, again, we can't actually plot the vectors, so we need some way of defining cosine in higher dimensional space. All right? And now we do some algebra, and this is a little bit confusing because we're using superscripts for the vector components, and we are using a superscript for the square. So the superscript outside of the parenthesis is the square. So if you write this out algebraically, we have the length squared of v minus u, which is just the sum of the squares of the individual components of v minus u. Right? So we know that the length squared, that basically you're taking the square root off in this case. The length squared of a vector is the sum of squares of components. So the length squared of this vector is the sum of squares of components. Then we're subtracting the sum of squares of components of this vector and the sum of squares of components of this vector. And if you do that out, when you do this square, you're going to get cross term, right? You'll get v1 squared plus u1 squared minus 2u1 v1. Now these are numbers v1 and u1, so we can define u1 and v1. All right. Now the v1 squared is going to cancel this one. The u1 squared is going to cancel this one. What you're just left with is the minus 2u1 v1. All right. So that's what we have here. Okay. So we have this. Now we have the sum of products of the components of u and the components of v. You may recognize this as u dot v. So that's what that is. And we're going to plug this into the, we're going to replace this with this quantity, and let's see what happens. Well, if you look at this expression here, this part here represents these three terms. Okay, so I should set this one equal to the remaining term, which is this. Now notice they both have a minus 2. So the minus 2 cancels, so we just get the sum of components is equal to length of u times length of u, v times cosine of theta. Okay. All right. So this is how we define dot product. Dot product is simply the sum of the products of components of the corresponding vectors. All right. So maybe you've seen that before, but this is how we get it in an abstract setting for n-dimensional vectors. All right. Now here we take the dot product of these two vectors, turns out to be 1 times 1 plus 2 times 1 plus 3 times 1, etc. So this is a sum of the numbers from 1 to 100. Okay. Now we have this notion of length here, x1 squared plus x2 squared plus x3 squared. That's the same as x1 times x1 plus x2 times x2 plus x3 times x3. Right? So in fact what you're doing here, let me write that out, just to make it more clear, we have x1 times x1 plus x2 times x2 plus x3 times x3. Now, you can write that as x1, x2, x3, dotted with x1, x2, x3. So now we can turn around and write length as a dot product. We define dot product using length. Now we can write length as a dot product. Okay, so the length is the square root of v dot v, and v dot v is going to be the sum of the squares of the components of v. So look at this example here. If I take the length of this vector here, what I do is I take the sum of squares of components, so that's 1 squared plus 2 squared plus 3 squared, all the way up to 101 squared. All right, and then to get the length, I have to take the square root of the result. All right. Now here's how we define angle. First we define cosine angle, and then we get angle in terms of that. Okay, so you could solve this for theta as u dot v over length of u times length of v, and you'll get the cosine of theta, and then to find theta you take the arc cosine. Okay, so if you have these two vectors here, you take u dot v, which is going to be 1 plus 3 plus etc. plus 101, and you have to divide by the length of u and the length of v. All right. Now, in 2 and 3 dimensions, we have a notice of perpendicularity or orthogonality. Now, we know that two vectors are orthogonal if the angle between them is 90 degrees. Now, cosine of 90 is 0. So, in 2 or 3 dimensions, if I have two vectors that are perpendicular, then their dot product is 0. You can verify that with the 1, 0 and 0, 1. If you take the dot product of those two vectors, 1, 0, and 0, 1, you'll find that the dot product is 0. And you have other cases as well. If you have, for instance, let's do another example of two perpendicular vectors. If I take the vector, say, I can take the vector 1, 1, so that would be 1, 1. And then here's the vector, this is going to be minus 1, 1. And these are perpendicular. If I take the dot product between these two, I'm going to get the first component times first component, so that's minus 1 times minus 1, minus 1 times 1, plus second component times second component, which is 1, 1. And that gives me 0. Okay, so here again we see that perpendicular vectors have 0 dot product. Okay. And that fits with our general notion that the cosine of the angle between two vectors is given by the dot product divided by the product of the lengths. Okay, so if the dot product is 0, the cosine is going to be 0. If the cosine is 0, then theta is 90 degrees. All right. Right. So here's an example of orthogonal vectors. Here, this is all ones. Here we alternate 1 minus 1. Okay. All right, now, in fact, there's a mistake here. It should be R100. If it's R101, it's not going to be 0 because you'll have an odd number of components. So a little mistake there. That should be R100. Okay. Now, dot product has some important algebraic properties, which you can verify. If you take the dot product of two vectors, doesn't matter which order you do, simply because you're multiplying the components together. Doesn't matter which order you multiply the components. Distributive, it's distributive because dot product is a component-wise operation. So the components will distribute, so the dot product also distributes. Okay, and you can similarly take this property because this property holds component by component, so it also holds for the entire vectors. Okay, so here you can dot on the left and distribute, or you can dot on the right and distribute. Positive definite, if you take u dot u, well, that's actually the sum of the squares of the entries of u. Now, if you take the sum of squares, every square is positive, so the sum of squares will also be positive. Right?